exercise. So the topic is optimization, and in your handout you should have basically the same information as to which steps we're going to be following when we're solving these questions. And like I said, this is a really interesting section. It's a little bit on the challenging side, but if you do lots of examples, I think it's a very fun section. You'll be amazed the level of problems you can solve here with a very basic information. And that very basic information is finding the maximums and minimums of a function. And how do we find them in calculus? How do we find maximums and minimums of a function? We just covered the graphing section, right? We did a lot of that, right? We set usually f prime equal to 0, right? Because that represents horizontal tangents on a graph, right? That represents points where maximums or minimums may be found. And we also, of course, sometimes do where f prime is undefined. But that's very simple equation. Solving f prime equal to 0 gives us some very important things about the function, and we're going to make use of that in this section. Okay, let's take a look at the steps of optimization. So basically, optimization is the process of finding maximums or minimums of a function depending on what is desired. For example, if you have a limited amount of material and you're going to create a can, let's say, from that material, maybe your question is, what should be the dimension so that I maximize the volume? You're trying to create as large of a can as possible from a limited resources. Or the question could be, let's say that you're talking about a profit function in business. How many items should I manufacture so I have the maximum profit available? And sometimes you're trying to minimize things. So say, again, it could be the materials. I want to create a box with a certain volume. How can I minimize the material use? How should I create my dimensions so I include that amount of volume in the container, but I use the least amount of material possible? So depending on the question, you're either maximizing or minimizing a given function, whether it's a profit function, the volume function, etc. And here are the steps that we're going to follow. First step is determine a function to be maximized or minimized. Read the question really carefully because they will tell you exactly what they want. If they want the maximum or the largest possible box, you're maximizing volume. If they want the least amount of material used, you're minimizing surface area. So read the question carefully. Usually they tell you exactly what they want. So write it down as a function. And then usually they give you enough information so that you can write that function in one variable only. So here you do a substitution. If there are two variables, get rid of one of them. And then the third step in every question is set the first derivative equal to 0. And here you're differentiating it with respect to x. Nothing is moving with time, like in the section related rates, you're differentiating with respect to time. Here you're just, it's like y equals f of x, like in the last section, like finding maximums and minimums of a function. You just differentiate the function with respect to x. You're trying to locate the lowest and the highest points of the graph, basically. So solve for x. And then once you have found that, it could be either a maximum, because solutions to that could be a max, or it could be a min, right? How do you know which one? Here is a suggestion that I have for us. There's more than one way. You could do the sign chart. If you're first increasing, then decreasing, it could be a maximum. But this is an easier way, I think. You don't have to do the entire sign chart. Whatever number you find in step 3, substitute into f double prime. If f double prime is positive, that means that the function is concave up. So the point you found would be what then? If the second derivative is positive, that means it's concave up, right? So the point found is going to be a minimum. On the other hand, if the second derivative is negative, then the function will be concave down and the point found will be a maximum. And usually step number 4 is a checking process. Usually by the time you get there, you already pretty much have a good idea about what the solution is. And also please read the note on the bottom of your sheet. Occasionally, the endpoints of the domain might also be used. Most of the time, the maximums and minimums are going to occur at the critical points. But there are very rare examples in the book. It might be like 1 or 2 examples in the entire exercise set where the actual maximum occurs at the end point. Now, have we seen an example like that in the last section under graphing? When we were finding absolute max and absolute min, right? what do? We check the function at the critical points, but we also check them at the endpoints of the domain, right? So sometimes that's also something good to do to make sure that you have really reached the absolute maximum. Or you can also look at a graph. If you do the graph and you can verify that the point that let's say you found a maximum and you were trying to find the absolute maximum. If you look at a graph, you will see that that is the absolute highest point on the graph. That can also verify that you have found indeed the absolute maximum, not just a relative maximum. Okay, we're going to do some examples. We're going to start with a very simple one that you don't even need calculus for. Most people guess this answer, but let's do it both ways. First by guessing and then by using calculus. That way, you will see that the methods we're using are really working, and then we can tackle more difficult examples. I want two numbers that add up to 20 and that multiply to as large of a number as possible. Okay. Before we do calculus on this, let's just do some trial and error. Okay. Give me two numbers that add up to 20. Any suggestions? We'll do a few trial error. 10 and 10 seems like the most easiest thing that comes to mind. 10 and 10. And what is the product there? 100. Right? Give me another possibility. 2 and 18, the product is 36, right? It's not as large as the previous one, right? You're trying to make the product as large as possible. 1 and 19, still the sum is 20, right? But the product is 19, not even close to the first one. So you could do all the, all sort of trial and error. It didn't even say it had to be whole numbers. You could try, 9.5 and 10.5 or things like that. But we have a pretty good idea. 10 and 10 is going to be hard to beat, right? It's a pretty large product. Now let's see what calculus tells us the answer will be. So you want two numbers. Let's call the numbers x and y. The sum should be 20. So x plus y must be equal to 20. The product should be as large as possible. So we want to maximize, and I suggest that you write this in every question. Write down specifically what is it you're trying to maximize or minimize. If nothing else, I will give you a little bit partial credit just for having gone that far in the problem. But most importantly, that will put you in the right direction to solve the problem. So always write down what is it you're maximizing. In this case, the product of the two. And the product of those two variables would be x times y. So if you like, call that the capital P function, or capital F, the function that we're trying to maximize. The product function, I call it f in this case. So in almost every one of the questions that you study in this chapter, you're going to have two lines when you begin a problem. Okay, one line, it says maximize this or minimize this. Okay, this is called your objective equation. This is what you're trying to maximize. Okay, then they give you extra information so you can solve the problem. The second one is usually called your constraint equation. They're giving you a condition that needs to be satisfied. Okay, so every one of these questions, whatever your objective function is, that's the one you're going to set the derivative equal to 0. Why? Because that's the one you're trying to find the maximums and minimums, right? So you need to know where those maximums and minimums exist. But before we can go to that, our step number 2 said, write the equation in one variable only. So let's do that. Let's write our objective function in one variable only. So f equals x times y. And instead of y, what can I write based on this equation? Y is 20 minus x. So basically, you come back over here, you solve for y up here, and then you substitute that back into this equation. And let's simplify it. The function we're trying to maximize is 20x minus x squared. Now tell me roughly, what's the shape of the graph of that function? It's a parabola that opens down because of the negative x squared, right? So there's going to be a vertex. The vertex will be the maximum. But in this class, we don't have to memorize the formula for the vertex because we can do it with calculus, right? We can take the first derivative set equal to 0. That will give us the vertex. That will give us the maximum point on that parabola. So whatever it is you're trying to maximize, remember, that's the function you're going to be differentiating and setting equal to 0. In this case, this is it. Let's go ahead and do the step number 3. Set the derivative equal to 0. So in this case, derivative is 20 minus 2x. set it equal to 0 and solve for x. So we get x is equal to 10. No surprises there, right? We expected to get 10 and 10. But for these questions, it's very important. Always go back and read the question. Make sure you're answering what you're asking for. In this case, they said, find the two numbers. So don't just leave with x equals 10. Go back and also find y. In this case, y is 20 minus x. It's also 10. And sometimes they will also ask you, they'll say, what is the largest possible value for the function? Like, what is the largest possible product? What is the largest possible box you can create, the largest volume in that case? In this case, they didn't ask it, but let's also say that the largest possible product would be 10 times 10 or 100. But remember the checking step, which is step number 4. How can be assured that the point we found is indeed a maximum and not a minimum? Because both a maximum and a minimum have its derivative, has its derivative 0 at a local max or min, right? So let's do step number 4, the checking step. Take the second derivative of the function, and what do we get? Negative 2, right? Which is a number less than 0 everywhere, no matter what x says, right? So what does that tell you about concavity? That it's going to be concave down, and that the point we found is going to be indeed a maximum. And since it's concave down everywhere, there's only one local max. It's also the absolute max. So we can't do any better than that. 10 and 10 are the best two numbers to select that will maximize the product as 100. Okay, so again, that question, we didn't really need calculus. We could have guessed the problem. Let's do another one of what I consider a basic solution, a basic problem, and then we'll move our way, to the more challenging ones. This one actually is not in your notes. I'm going to just write it right now. It's a very similar one to the one we just did. The question is, the sum of two positive numbers is 9. The sum of two positive numbers is 9. Find the numbers if the product of the square of the first and the second is a maximum, is as large as possible. So the sum of two numbers is 9. Find the numbers if the product of the square of the first and the second is as large as possible. Once again, we're dealing with two numbers, right? So let's call them x and y. Let the numbers be x and y. What do I know right away? They add up to 9. So that's my first equation. X plus y is equal to 9. And then they tell us that the product of the square of the first and the second should be as large as possible. So as large as possible meaning maximize, right? Maximize. What are we going to maximize here? The square of the first, which is x squared, if you say the first number is x, and the second, but they didn't say the square of the second, so it's just the square of the first number and multiply with the second number, so times y. So we're trying to maximize. Remember, every one of the optimization questions that you solve, you should have an objective function, and next to it you should write down maximize or minimize. Many times what I find is like students have difficulty because they have two equations and they forget which one was I was supposed to maximize, which one I was minimizing, and then they go back to the wrong equation, and then everything goes down the hill from there. So write down which ones you're maximizing. This is your objective function. This is the one you want to get in one variable only. Okay, x squared times y. Now you have two choices here, right? You can either solve for y on the top, or you can solve for x. But one is going to be easier. Any guesses which one is going to be easier? You think of the next step when you substitute it back in. Is it easier to substitute something for x or something for y? Easier to substitute something for y, because otherwise you have to binomial square the quantity. You know, that's going to be messy. So let's solve for y then in this equation. Y equals 9 minus x. So we're trying to maximize. Once again, let's call that function f. You could call anything you like. So the function we're maximizing, our objective function, is x squared times y. And instead of y, what am I going to write? 9 minus x. Okay, what should I do at this point? Distribute it. So we have 9x squared minus x cubed. This one does not have such an easy graph to guess, right, because it's a cubic. Okay, what do we do now? Take the derivative and set it equal to 0. So the derivative is (18x minus 3x squared), right? Differentiate with respect to x. And what am I going to do with the derivative? Set it equal to 0, because we're looking for points where slope is 0, where the maximums might be occurring. Again, normally critical points can also come from points where the function is, the first derivative is undefined. But for polynomials, they're always defined, so there's nothing to worry about that. Okay, let's try to solve this for x then. Take out a 3x. So we have a 6 from the first one and minus x from the second one. Okay, so we now set each one equal to 0. What do you get from the first one? You get x is equal to 0. And what do you get from the second one? X is equal to 6. Okay, if x is 0, what is y? Because earlier we said y is equal to 9 minus x. If x is 0, y is 9. And if x is 6, what is y? 3, right? Now, so it's either this pair or this pair. One could be max and one could be minimum. So our checking process will be helpful here. So let's go to step number 4, where you check for the second derivative of the function. Check the second derivative. What is the second derivative of this function? Take it from here, differentiate it one more time. Derivative of 18x is 18. Derivative of negative 3x squared is negative 6x. Now, this is not going to be positive everywhere or negative everywhere, because there's an x in it. So what we should do is, the two values that we got up here, we got this one and we got this one. One at a time, let's plug it in. Okay, so first evaluate this at the point x equals to 0. And what do we get? We get 18, which is greater than 0, right? Positive. So that means that the function's concave up. At that point, you're going to have a minimum. Then take the same second derivative function. This time substitute which number? 6. That'll be 18 minus 6 times 6. So that will be definitely a negative number. What is it, negative 18? So definitely, again, you don't even care what number it is as long as it's positive or negative. Negative means concavity will be downwards, and the point obtained will actually be a maximum. Okay? So we want to keep the 6, which comes, of course, with the pair of 3 as the second number. So we're saying that if the first number is 6 and the second number is 3, you will have the largest possible function f. And what would be the largest possible value of f in this case? If x is 6 and y is 3, remember the function was you multiply the square of the first times the second, right? And the first number is what we called x. So you're going to multiply the square of that times the second. And I believe that turns out to be 108. So this is the highest value for the function. So if you try any other combination of two numbers that add up to 9, x and y that add up to 9, we expect that we're going to get something less than 108 when you put it into x squared times y function. So the question was, what are the two numbers? And our answer is, the two numbers are, the first number is 6, and the second number is 3. Those are the two numbers that the question was asking for. Okay, next we're going to do something from your handouts. I believe this is the rectangle problem. What number is that? Let's see, example number 3 in your handout, the fencing problem. Okay. So I'm going to do the picture, then I want to give you a little bit of time to think about it, and then we'll discuss it together. Suppose we have 200 feet of fencing available to enclose 2 adjacent rectangular fields. And these are supposed to be of equal sizes. The question is, what dimensions for the rectangle would yield the largest possible area using the limited fencing material? So you are restricted by this 200 feet of fencing. Like one very extreme situation, something like this. Use your fencing to do something very thin and very long, right? You could do something like this, but usually when you do extreme things like this, you don't end up with the optimal solution. Like this is not going to be the one that gives you the highest possible area. Usually, and you could do something very thin and long that way. Again, that's kind of almost the same, saying the same thing. Usually the optimal solution is somewhere in the middle, the one that will give you the maximum possible area. Now, so that we can all start working with using the same variables, let me also assign the variables, and then you can take your time to work on this question. Let's say that the width of this outer rectangle is x. So these are x units. And let's say that this the length of the rectangle is y. Again, you could have done this in a number of ways. Like you could have called the smaller side, just this side being y. You could have given different variable names. But if we all start with the same variables, it'll be easier to compare your answer against my answer later. So let's just assume this. So I'm going to give you a little bit of time to work on it, and then we'll come back. So again, earlier we wrote down that the fencing is 200 feet, which corresponds to the perimeter, which is going all around these fields. We have a total of 2y plus 3x. That must be equal to 200 feet of fencing. And we're maximizing the area, so that's the total area of the entire region. That's the length times width of the outer rectangle, which is x times y. Once again, this is our objective function. It has two variables. We need to get it down in one variable. So I'm going to solve for y in the first equation. So I have 2y equals to 200 minus 3x. And then divided by 2. So y equals 1/2 of 200 minus 3x. Or just everything divided by 2. Of course, you could have also solved for x in this equation. Either one will be just as easy to substitute back in your objective function. So in this case, area equals x times y. But we now know what y is. Y is 1/2. You know what? I'm going to go ahead and distribute this and then put it down there. So 1/2 times 200 is 100. And then minus 3 over 2x. That's what y is. And since area is x times y, now I'm ready to put the y into that equation. And as always, we simplify this function first before we differentiate. Okay, now that we have an objective function in one variable in simplified form, what do we do to this? Set the derivative equal to 0. Take the derivative exactly. So take a prime, find a prime. Again, that's really the essence of all of these questions. A simple idea. Setting the derivative equal to 0 is solving these like a large number and type of problems, which is, I think, one of the things what's amazing about this section. It's like the range of problems, like you cannot imagine. When you look at the homework problems, you will see how many different types of questions you can solve with this basic idea. Okay, so derivative of the first one is 100. The next one is minus 3x. Set it equal to 0 and solve for x. You will get 100 is equal to 3x. X is 100 over 3. When you take the derivative of this term, bring the 2 down, right? So you have 3 halves times 2. The 2's cancel. Okay. So at this point, you can convert to a decimal, or if you like, keep it like this at the moment. And then you can, so that way you don't have to do rounding errors. So let's find y now. If you like, before we even find y, let's just check and make sure this is what we were looking for. This is indeed a maximum. So take the second derivative. The second derivative is negative 3, which is a number less than 0. That tells you it's always going to be concave down, and the point found is indeed a maximum. So now we can go and find y. Y equals, I'm going to go with this equation. Y equals 1/2 times 200 minus 3x. X is 100 over 3. The 3's cancel. I have 200 minus 100 inside the parentheses. That's 100 outside waiting to be multiplied in is 1/2. And 1/2 of 100 is 50. And the units, everything was in feet, I believe. So the units will be in feet as well. So we're saying that the dimensions of the rectangle should be 100 over 3 is roughly 33.33 feet by 50 feet. Yes. What was a double prime? If this is your a prime, differentiate it one more time. And the 100 disappears, you were left with negative 3. So for this question, there was not even an x in the equation for a double prime. So it's always negative. It's always concave down, basically. And sometimes they might also say, you know, what is the largest possible area that you can create two adjacent fields with 200 feet of fencing? In that case, you should also go ahead and multiply the x times y and also report the final answer as an area figure. So again, it wasn't asked here, but if you were to do that, let's just do it for the sake of this example. So 50 times 33.33 roughly is 166.5 roughly square feet. So this is the largest area that you can create with the given amount of fencing and with the criteria that you need two adjacent fields made with that fencing material. Okay, any questions about this one before we try another one? Any questions? Okay, so on to our new example. Not that one. Let's go back, I think. There we go. So we're going to make a box out of an 8.5 by 14 sheet of paper. So we have our legal size paper. And we're going to make this box by cutting off the corners and then folding the sides up. So what's remaining is basically this is remaining, and so are these sides. Now if you fold the sides up, you will end up with a box. So roughly speaking, not up to scale or anything, but I'm just going to do a box here. So what I would like to write down, and the question says, what should be the size of the cut x? So if you call this x by x, it's a square piece of paper we're cutting from each corner, then we're folding the sides up. So basically, like you're folding this up and this up, etc. So then you end up with this one. So what should be the size of the cut? So that we end up with the largest box possible. And then they want to know what are the dimensions of the box that you can form for the largest possible box. So first question is, what is it that we're trying to maximize here? The volume. Largest box means maximize the volume. So we want to maximize volume. Volume. Now, volume, we need to write an equation for it. And the only thing we know is really the outside dimensions of this paper. Like this side was, to begin with, this side was 8.5. And this side was 14 inches. Now, when you cut it, x from here, how much are you left with then for this side of the base of the box? That's, let's say this is the same as this. Would everybody agree? 14 minus 2x, you're cutting x from here, x from there, so that side will be 14 minus 2x. Okay. And what about over here? What are you left with there? 8.5 minus 2x. Okay. And what about the height of this box? When you fold these sides up, what will be the height of the box, which is the same as this? X. The cut becomes the height, right, as I showed you in that figure earlier. So the height of this box will be x. So what can you say then for the volume of this box? Volume in general is length times width times height, right? Volume is length times width times height. So to do that, let's just multiply these three dimensions together. We have x times 8.5 minus 2x times 14 minus 2x. Okay, do we have one or two variables in here? Only one, right? The only unknown is x, right? So in that regard, it's easier. You don't need another equation to get rid of the x. The only thing is this is going to be a little bit messy to multiply. That's the only problem here. But you don't have to basically try to get rid of one variable because you only have one variable, not two variables. So let's go ahead and multiply this out. So volume equals, first I'm going to multiply the x in, which is 8.5, just with this one. 8.5x minus 2x squared. And then we still need to multiply that with the second binomial, which I will do in the next step. Okay, so let's try to do this like a FOIL. So we're going to go, or just go in any order you like. So like 8.5 times 8.5x times 14. Let's see what that is. 8.5 times 14 is 119. So we're getting 119x. Then do 8.5x times negative 2x. Negative 17x squared. Then do this times that. Negative 2x squared times 14. That's negative 28x squared, right? And then do the last ones. Negative 2x squared times negative 2x, which is positive 4x cubed. Can we clean this up a little bit? Can we? The x squared terms we can simplify a little bit, right? So I'm going to also put the highest degree term first. That's 4x cubed. What do you get when you combine negative 17x squared minus 28x squared? Minus 45x squared. And the last one is plus 119x. Now that we have our objective function, we want to maximize the volume, right? We're trying to create the largest possible volume with the same sheet of paper that we have been given. So now the question is, what do you do from this step forward? Okay, so before we do that, okay, so what are we going to do with this? Take the derivative, set it equal to 0, just like our other problems that we have been doing. Okay, take the derivative and set equal to 0. So let's differentiate. We get 12x squared minus 90x plus 119. Okay, I wouldn't even attempt to factor this one out. Numbers are too large, too many possibilities, or it doesn't look like it's going to factor because of that 119 seems such an odd, weird number that may not even have any factors. So what is our alternate route then? If we're not going to factor it, let's use the quadratic formula, which says negative of b plus or minus the square root of b squared minus 4ac, everything divided by 2a, and 2 times 12 is 24. Okay, I'm going to give you a moment. There'll be two answers from here. I'd like to hear both of them. 1.71 for one of the solutions. And what about the other one? I think 5 point something. Good, 5.79 roughly inches. Okay, once again, two answers. Which one do we want? Let's go to the second derivative. As a matter of fact, for this question, you don't even need the second derivative, although we're going to do that. But take a look at the cut of size, roughly 5.8 inches. You know, the width of this paper was 8.5, right? If you cut 5.8 from here, 5.8 from here, there's no paper left even, right? So that solution is not even in the domain of the problem situation. But if you didn't catch that right away, do the second derivative test, and that will tell you that there is going to be a minimum, basically. That's going to give you a negative volume or something like that. But again, in this case, 5.79 is way too much of a cut. You're going to end up with having no papers at all. So that one we can automatically eliminate, or going to the second derivative test, find the second derivative, 24x minus 90, plug in 1.71 first, and then plug in 5.79. And all you have to care is positive or negative. When you plug in 1.71, what did you get? Exactly. So basically, all I'm interested in is that it's a negative number. It's less than 0, meaning it's concave down, and the point obtained there will give us the maximum volume, right? Right. We always plug them into the second derivative. Right. The 1.71 made it negative, right? V double prime evaluated at 1.71. That one was negative. What if, when you evaluate into the 5.79 into the second derivative, what do you get there? You'll get a positive answer, right? That means there is concave up, and that point would be a minimum, so we don't want that one. So we're going to eliminate this one, and we're going to keep the other one. So we're saying that x should be, the size of the cut should be 1.71. Remember earlier I showed you 3 boxes? The best one I showed you, that it was a cut of 1 inch, 2 inches, and 3 inches. The one of 2 inches was the best one, 90 cubic inches. Let's see if this one beats that. Okay, so if you have a cut of 1.71, what will be the volume of this box created? The volume will be, so you have to multiply 3 dimensions, right? One dimension will be 1.71. What about the other dimension? Do 8.5 minus 2 times 1.75. So that dimension seems to be 5.08. And the other side, do 14 minus 2 times x. And that dimension seems to be 10.58. Let's see if we did any better than 90 cubic inches. That was the first estimate I had given you. So multiply these 3 numbers together. Did we do any better? What is the product? So we did a little bit better, 91.9, roughly 92 cubic inches. So the dimensions are these, and the maximum volume you can obtain with that sheet of paper, if you're going to be cutting from one of the corners, the maximum volume you can create is 91.9 inches, cubic inches. So this is the typical Coke can question. It really includes 355 centimeter cube or milliliters of Coke. The question is, how would you select the dimensions, radius and height, so that we want to minimize the amount of material used? So once you've made a decision, you're going to include this amount of liquid in a container, and you know that it's going to be a cylinder. That's a given. The question is, what dimensions? Because one possibility is you could make it really shallow, something like this. You could create a container, a cylindrical container like that, that will take 355 milliliters of liquid. But for one thing, for human beings, it's not very convenient. You got to hold with 2 hands or something, very shallow, it'll spill, it's not going to work out. Or you could do something very thin and very long, something like this. Again, storage will be an issue, and again, it's not very convenient for human beings. Plus, these extreme regions usually use the most amount of material. It's not going to be you're minimizing the amount of material used. We want to include the 355 milliliters of liquid. At the same time, we want to keep the amount of material used to a minimum. So let's just do a reasonable looking size here. We don't know the exact dimensions right now, but we don't think it's going to be any one of these extreme cases. All we know is that it has to be a cylindrical can. Let's say the radius is r and the height is h. So let me remind everyone, and it's important to know for a cylinder, for a cone and sphere, I would give you the formulas, but I want everyone to be very familiar with a cylinder, a box, especially area and surface area and volume. Okay, so in this case, what is the volume of this cylinder? Let's just remind everybody what the formula for the volume is. You're thinking about the cone. This is easy because it's just going to be area of the base times the height. What is the area of the base? What is the area of a circle? Again, this is very important. Everyone should be familiar with the area of a circle is pi r squared, if the radius is r units. And also everybody should know, what is the circumference of a circle? 2 pi r. If you have forgotten, please make sure you review that. Very important. It will come up a lot in this section. Area is pi r squared, circumference is 2 pi r. For this question, to find the volume, you want area of the base times the height. Area of the base is pi r squared. And the height is this h. Right. So that means the volume will be pi r squared h. That's the volume of the cylinder. When you're minimizing the amount of aluminum used, I even put in parentheses, basically you're trying to minimize the surface area. So let's also recall, what is the surface area of a cylinder? This one is a little bit harder, but I still expect you to know it, especially after you see the following, demonstration. Open that Coke can as if you're just cutting it from the middle and opening it up. Okay, when you open it up, so if you were to cut it from here and open it up onto 2 sides, you will have a rectangle. What is the length of that rectangle? What would be the side? That came from your circular portion when you opened it up. Basically, this became the length of that rectangle now. So what is the length of that rectangle? 2 pi r. What about the height of this rectangle? When you open this up, the height is still h, right? Because you basically opened up that body of the Coke can, not the top, not the bottom circles, but you opened the lateral side, and the height is still h. So basically, the Coke can consists of this body, the middle portion, plus 2 circles, right? A circle for the top and a circle for the bottom, right? This is the surface area of the Coke can. What is the area of the top or the bottom of this can? If the radius is r, the area will be pi r squared for this one. What about this one? Also same, right? They're symmetrical, pi r squared. What about the area of the lateral side? the round portion that goes around the Coke can. What is the area of that portion of the can? This now is a rectangle. Area of a rectangle is length times width, right? So what will it be? 2 pi r h. So all of this is your surface area equation. So I'm going to rewrite it over here. Surface area of a can equals, simplify for me, pi r squared plus pi r squared, that is 2 pi r squared, plus this one, which is 2 pi r h. Okay. Now the question is, which one of these? Do you want this one maximize or minimize, or this one maximize or minimize? Would you read the question and tell me which one is my objective function? Surface area. And what am I supposed to do with that? Maximize or minimize? Minimize. You want to use as little amount of aluminum as possible. So we want to minimize surface area. So minimize this. This is our objective function. It's so important to write next to it, maximize or minimize, so you automatically know this is what I'm going to minimize. This is the one I need in one variable, and this is the one I'm going to differentiate and set it equal to 0. So this is the objective function. That's the one we're minimizing. Okay, but what extra stuff do we know? We know that the volume of this container is how much? Volume equals 355 centimeter cube. So volume, which equals, we just refreshed our memory about that, pi r square h, that should be equal to what? 355. Okay. So I'm going to give you some time in your groups to work on this, but what will you do next? Just tell me in words, please. Okay, so you have a choice. You could solve for h or you could solve for r. It's going to be easier to solve for h, so I agree with you. Solve for h in this equation, and then what you're going to do with that? Put it over there, and then what? Take the derivative, set equal to 0, and then do your checking with the second derivative, okay? So after you do this question, I want to be able to give you one more in your groups, but let's start with this one. Okay, let's go ahead and complete this question for the sake of our online students. So previously we had obtained the following information, that the volume for this can is pi r square h, and that is a given quantity. It has to be 355 milliliters or centimeter cube, and they want to use as little as possible, as little of aluminum as possible to create this can. So we want to minimize the surface area, which was given by 2 pi r squared plus 2 pi r h. Now we need to get our objective function, which is this one, in terms of only one variable. Currently we have r and h, so we'll come to this equation to help us with that. Solve for h in this equation. H equals 355 over pi r squared and take that information, plug in into our surface area function. So surface area now equals 2 pi r squared plus 2 pi r h, where h equals 355 over pi r squared. And let's get rid of the pi's. One of the r's can also be canceled, taking away this power here and rewriting our surface area. We get 2 pi r squared. 2 times 355 is 710. I get plus 710 over r. Remember, this is the function we're trying to minimize, and we already got it in one variable, so now we need to differentiate it and set it equal to 0. So the derivative of the surface area function equals 4 pi r. And to differentiate 710 over r, you can write it as 710 times r to the minus 1. So the derivative will be negative 710 r to the minus 2, which is really the same thing as divided by r squared. Now we set the derivative equal to 0 and solve for r. The easiest way is put the second term on the other side, multiply both sides by r squared. So now you'll have 4 pi r times r squared, so that's 4 pi r cubed. On the other side, when you multiply it by r squared, the r squares disappear. You get 710. Now divide both sides by 4 pi. So we have 710 divided by 4 pi. And finally, take a cube root. So r equals the cube root of 710 divided by 4 pi. As I was going around the class this morning and answering some questions, I noticed a lot of people made a mistake entering this into the calculator. Remember, when you are dividing 710 by 4 pi, make sure you use a parentheses for the denominator. You're dividing by 2 factors, so division, open a parenthesis after the division sign, then put the 4 pi in there, close the parentheses. So that ratio should be roughly 56.5. So you should be taking the cube root of 56.5 roughly, and that you can do either by raising to the 1/3 power or under math. I think there is a cube root sign in there. Cube root of 56.5 is 3.83 roughly. So the radius is, let's say 3.84 centimeters. It's centimeters because 355 milliliters could also be written as centimeter cube. So if the volume is in centimeter cube, the length will be in centimeters. And finally, to get h, go back to your h equation, which was 355 divided by pi r squared, and substitute your r equals 3.84, and you should get 7.66 centimeters for the height of the cylinder. And if you check what these dimensions mean, like if radius is 3.84, multiply that by 2 to get the diameter of the Coke can. So it's less than 8 centimeters. It turns out that this is actually a little bit wider than a typical Coke can. And then the height is 7.68, and the height is a little bit shorter than a typical Coke can. This might be maybe some of the soup cans maybe they have, but it looks like in the design of the Coke can they did not really use calculus. However, if you look at the Coke can in more detail, you will see that it was not a perfect cylinder to begin with. That on the upper and the lower ends, it's like the ends are bent in circular motion. It's not a very flat cylindrical top. It's a little bit bent. So if next time you drink a can of soda, look at the design of this can, and you will actually see it was not a perfect cylinder to begin with. All right, so I would suggest that you solve lots and lots of questions on optimization now to get more familiar with this topic. A good place to begin might be our group activity problems, the first sheet. There will be another lesson on optimization, and the second sheet on optimization problems can be done after that second lesson. Of course, you also have plenty of questions from the textbook.